Okay, hi everyone. Nice to see you all again. Hope you're all surviving. Hope the smoke isn't getting to you. If you're in the Bay Area, if you're elsewhere, lucky you. Unless you have smoke there too. Unless you're in Oregon or something, in which case, unlucky you. So, last time we first covered QKD using Bell states. Where the basic idea was that if you had some Bell state shared between Alice and Bob, and they did random measurements on that Bell state in either X basis or Z basis, then that state was the only state that has perfect correlations for both of them. And so for Eve to learn anything about what's going on with the measurements, she would have to in some way entangle her device with the Bell state, but then it wouldn't, the state wouldn't be just in that one Bell state, and so the correlations wouldn't be perfect, and so Alice and Bob would be able to detect that sometimes they got disagreeing answers, and so something was going wrong when they tested a few qubits. Okay, and then we moved on to talking about unitary gates. We had a load of examples. Pauli matrices. So X basically acts as a NOT gate, taking 0 to 1 and 1 to 0. Z acts as what's called a phase flip, applies a phase of -1 if the state is 1 and not otherwise. We had the Hadamard gate, which basically just swaps the X and Z bases. And the other very important gate we introduced, which was a 2-qubit gate, it's called the C0 gate, which basically applied an X gate to qubit 2 if and only if the first qubit, the control qubit, was in the 1 state. Okay, and in particular, I try to emphasize that classically, this would mean that the C0 gate didn't do anything to the first qubit, but because these things are being applied in sort of coherent superposition, quantum mechanically, then when we apply states that are in some different bases and things like that, then the control qubit can actually get infected. Okay, and in particular, if you take a C0 gate and you sandwich it with Hadamards on both qubits, then it actually turns into a C0 gate with the 2 qubits reversed. So the control qubit is getting just as affected as the target qubit. And final important thing that I introduced last lecture was just this notational thing, but it's very powerful notation, which was circuit diagrams. And remember that in circuit diagrams, each line represents a different quantum system that's all getting tensor producted together. Often they'll represent individual qubits. And then you sort of have boxes that maybe get called U, and that means that some unitary U is getting applied to those qubits, to those quantum systems. Okay? So Thursday was a less exciting lecture because there was a lot of introducing stuff rather than using that stuff to do anything terribly interesting. Today, we're going to get some cool applications of quantum circuits. The first is possibly the most sci-fi sounding thing in quantum mechanics, which is quantum teleportation. It's both less cool than it sounds in a sci-fi sense and also more cool. Yeah, it really is quite exciting. I like it a lot. So it sort of shouldn't be possible to do, but it is. And the second is in some sense a sort of reverse version of quantum teleportation called super-dense coding. Okay. Okay. So on homework 2, you guys proved, hopefully, that there's no copy and paste with quantum states, right? It's called the no cloning theorem. It's just a fact that a map, the map that copies a quantum state into the tensor product to do things is nonlinear, so it just can't ever be done quantum mechanically. It can't ever be unitary for a start. The natural question is, if we don't have copy and paste, what about cut and paste? Okay. So, yeah. If cloning is impossible, what about like just deleting it from one place and creating it instead somewhere else? And this is certainly possible. One very simple method of doing it. So say we want to Bob has a qubit, he wants to cut his qubit, delete his qubit, and then paste something over with, sorry, Alice has the qubit originally, she wants to cut it and then paste it with Bob. The easiest option is just Alice sends a photon, say, to Bob, or some other physical implementation of a quantum qubit gets sent from Alice to Bob. Okay, so we store the qubit we want to send in that photon or whatever it might be, and then we just send it. And to send a qubit, you have to be kind of careful because it's easy to have like noise and stuff like that, destroy the qubit, but you can do it. It's been done many times. And there we go, we've done cut and paste. But as I say, sending qubits is hard. You need some, you need to make sure that the qubit doesn't get measured anywhere along the route or doesn't interact with anything, because that will screw it up. So a natural second question is, what about if we can only send classical bits, sometimes called C bits? From Alice to Bob. Okay, so this one seems a lot harder, right? Like, just to describe the state of a qubit, describes psi, I would formally need, to describe it with infinite precision, I'd formally need infinitely many classical bits. And even if I just wanted to describe it with very high precision, I need a large number of classical bits. And moreover, if I just have that assumes I have a description of the qubit, right? If I just have the qubit itself, then with a single copy of a qubit, as we've seen, I can't work out exactly what the state psi was. All I can do is like measure it in one basis, right? And then I get a single classical outcome, and then if I measure in a basis again, I've lost all the information about what the original state was. So this seems totally impossible. It seems like the best you could do is just pick a random basis and then send the measurement outcome, and then you've you've got some estimate of the state in that basis, but you've destroyed the superposition. Okay.
So
Despite the fact,
is a quick question: is the issue here that that you as like Alice say don't know with 100% what your state is?
Yeah,
Because,
exactly.
okay.
So yeah. So if I have a mathematical description of the qubit, if I know, say, if I have some state psi alpha 0 plus beta 1, and I have the two complex numbers alpha and beta written down to some number of decimal points, then I can just send that message to Bob. He can prepare the state himself, and we're all good, right? But what we're wanting to do is we just want some like quantum algorithm that we have this physical quantum state that's in some state psi, but we don't know what it is. And by doing measurements or applying unitaries to it or something like that, applying some quantum circuit, and then sending some classical information to Bob is going to be able to end up with the state psi. Okay, that's the thing that seems like it should just be impossible. Is that clear?
Yes, thank you.
Awesome. Okay. turns out actually is possible so long as Alice and Bob share a bell pair. And the way you do it is this thing, quantum teleportation. Okay. So let's start with, before we actually talk about how to do quantum teleportation, let's start with something very simple, which is an even easier circuit. Just how to make a bell pair, okay? Because presumably the way Alice and Bob are going to end up sharing this bell pair is sometime in the past, they were met up, had their 2 qubits, you know, done some operation on those 2 qubits to turn it into a bell pair, and then one of them takes each qubit, okay? So anyone want to give a suggestion for how we can make a bell pair using some gates that we've already seen? So of all the gates written up here, we have X, we have Z, we have the Hadamard, and we have a C0. Can anyone say one of those, if we're just going to use some combination of those 4 gates, what's one that we definitely need to use? If we start with 2 qubits that aren't entangled and we want to end up with a bell pair?
C0.
Awesome. So why is that?
Because it's the only 2 qubit gate on the list.
Awesome. Right, so if we start with a product gate and we just apply a unitary to 1 qubit, we're still going to have a product state, okay? But if we apply a 2 qubit gate like C0, then we can create entanglement between the 2 qubits. And the particular circuit that will do this, really very simple. So we start both qubits in the 0 state. We're going to apply a Hadamard gate to the first qubit. Then we're going to apply a C0 that is going to be controlled by the first qubit and have target second qubit. And then that's going to be it. Okay? So let's sort of track what this circuit does by looking at the state at each sort of intermediate time step. Okay, so at time t0, the state is just 0, 0. That's what I told you, the initial step. What about at time t1, after we apply a Hadamard? Someone can tell me? What does the Hadamard do to 0 state? Yep.
Plus and 0.
Yep, awesome. Hadamard switches the plus minus basis with the 0, 1 basis. It's going to create the state plus 0. Or equivalently, just to write this out very explicitly, finally, we need to apply C0 gate to the 2 of them. What does C0 take 0, 0 to?
0, 0.
0, 0 stays 0, 0 because the control qubit is in state 0. What about 1, 0?
1, 1.
Goes to 1, 1 because the control qubit is in 1, state 1, so the target qubit gets flipped. Sorry. I say that while writing the wrong thing. Okay. So there we go. That's a very simple circuit that will make a bell state. There's actually an even simpler notation we often use, because bell states are useful things that show up a lot. Which is we say, this is just equal to something that looks like this. This is not, this is not some circuit. This is just notation for specific notation that we use for roll state. And so the reason this is sort of sensible notation is that if we just had a line going from left to right, that would just mean the identity matrix, okay? So that would be 0, 0 plus 1, 1, the identity. Now what we're doing, so this line has sort of, it's always pointing left to right? So it has one draw and one ket. Now we've turned it round, we just bent the line round so that it now has 2 kets. So we interpret that, and again, this is just convention, as we turn round the bra part of the state, so it becomes 0, 0 plus 1, 1, i.e. a bell state. Okay, so that's just the reasoning behind that notation, but it really is just a convention that we use that to represent a bell state. Okay.
Quick question. In
Yes.
these sorts of diagrams, is it always assumed that the state that coming out is normalized properly?
Yeah, exactly. So sorry, I should say, normalization is just a convenient convention that makes things easier to calculate with. So again, we assume this state is normalized when we're doing calculations, but if it wasn't normalized, it's still the same state. Okay,
I'm imagining this sort of thing as part of a larger circuit with other bits, and so that case you do need to worry about normalization.
No,
right?
because it's getting tensor producted with other bits, right? So if one of your states in the tensor product is not normalized, then it's the overall state is just not normalized, but it's all fine. If we took a superposition of different things where one of them, then the normalization would matter, right? But we can't do that. So the way that the notation works is anything else will be tensor producted with. Okay, but just think of it as representing the normalized state. It's just notation. It can mean whatever we want to mean. Okay, so in quantum teleportation, the starting setup is that Alice has some qubit in some state psi, okay? And then Alice and Bob share a bell pair, okay? So one of the 2 qubits in the bell pair is held by Alice and one is held by Bob. Okay, and now we want to do a circuit where we're going to end up with Bob having qubit in state psi, okay? And I claim that in fact you can do this by only sending 2 classical bits from Alice to Bob, which is really quite crazy, and it's amazing that it's possible. And the circuit that's going to do this is going to be really quite simple. We're first going to apply a C0 gate controlled by Alice's qubit in state psi, okay, that acts on her half of the bell pair. Again, you'll see, the thing that we're wanting to eventually send over to Bob is acting as the control qubit, but stuff is still going to happen to it. Now, just going to apply a Hadamard to that qubit. And then we're going to measure each of them. Okay, so this is just going to be notation, this little measuring dial that just means measure in the computational basis, 0, 1 basis. Normally in quantum computing, rather than worrying about which basis we're measuring, we'll just apply unitaries as necessary to get the basis we want to turn into the computational basis, and then just measure in the computational basis. So now we have Bob's half of the qubit sitting down here, and we have the 2 qubits up here being measured. So we just have some classical outcomes that we can call M1 and M2. Okay, so these double lines represent classical bits. So these classical bits get sent over from Alice to Bob. And then using those classical outcomes, we're going to apply a unitary to Bob's qubit. Specifically, we're going to apply a bit flip x to the power M2, i.e. we're going to apply it if M2 is equal to 1 and not otherwise. And then we're going to apply a phase flip if and only if M1 is equal to 1. Okay, we're left with a qubit here, and I claim that that qubit is going to end up being in the state psi. Okay, everyone clear what the claim of this circuit is? You should not be clear at all like why it works. We're going to see that in very explicit detail. We're just going to go through the steps. But are people clear on what I'm claiming happens and what the setup is? Okay, everyone's either clear or shy, so that'll have to do.
So just really quickly, just to make certain, the X's and Z's at the end, that's saying it flips if M2 is equal to 1.
Yeah, exactly. So we x to the power, we apply the unitary x to the power M2, right? i.e. we apply x if M2 equals 1, we apply the identity of M2 equals 0. Okay, so Bob just has some classical numbers and he just applies a unitary depending on what they are. Okay, so let's do our usual
the claim
strategy.
is that Bob now has psi.
Yeah, the claim is that the Bob is going to end up with psi. So I'm just going to draw all the different intermediate times in. And we're just going to track the state all the way through the process. Okay. It's going to be helpful to expand psi as alpha 0 plus beta 1, as usual. Okay, so at T0, our state is alpha 0 plus beta 1. It's 1 over square root 2, 0, 0, plus square root 2, 1, 1. Okay, that's our initial state. Now at T1, we need to have applied a C0 gate where the control qubit is this initial qubit, the first qubit, and the target qubit is the second qubit. Okay? So we're going to have 4 different terms here. Okay, so we have alpha over square root 2, 0, 0, 0. Anyone going to tell me what that's going to go to? Come on, guys, someone say this. The input 0, 0, 0, go ahead, sorry.
0, 0, 0.
Yep, right, the control qubit is in 0, so nothing happens to the target qubit. So we still have 0, 0, 0. We also have alpha 0 times 1 over square root 2, 1, 1. Okay, so that's alpha over square root 2 times 0, 1, 1. What's going to happen to 0, 1, 1 when we apply the C0? Again, nothing because the control qubit's in state 0, so it's going to stay as 0, 1, 1. Then we have the beta terms. So we have beta over square root 2 times 1, 0, 0. What's going to happen to 1, 0, 0? Come on, someone.
Will become 1, 1, 0.
Yep, awesome. So the control qubit is in 1, so the target qubit gets flipped, so we get 1, 1, 0. And we have beta over square root 2 times 1, 1, 1. What happens to that? Come on, guys, just shout out. We'll make this faster.
Will become 1, 0, 1.
1, 1, 1 becomes 1, 0, 1 because, again, control qubit is in state 1, so the target qubit gets flipped. Okay. Seemingly, we now have some sort of complicated seeming state. Yeah, it doesn't seem like we've made terribly much progress yet, but we're actually starting to. Let's now go to T2. Okay, so what happens to T2? We apply a Hadamard gate to the first qubit. Okay? So now, yeah, it's going to seemingly become a bit messy. So 0 is going to go to 1 over square root 2, 0 plus 1. 1 is going to go to 1 over square root 2, 0 minus 1. Okay, again, this is just for the first qubit. The other 2 qubits aren't having anything done to them, so they'll stay the same. So I'm just going to write down all these terms because there are quite a lot of them. So we now have alpha over 2 because we have an extra factor of 1 over square root 2 showing up. We have 0 goes to 0 plus 1. So we have a 0, 0, 0 plus 1, 0, 0. And we have plus 0, 1, 1 plus 1, 1, 1. And we have beta over 2, 0, 1, 0 minus 1, 1, 0, because we started with the first qubit in state 1, so it went to the minus state, and then again, plus 0, 0, 1 minus 1, 0, 1. Okay. So that's pretty huge, but don't worry, because we're about to do some measurements, and that's going to get rid of a lot of these terms, okay? And then it's going to get a lot simpler. So at T3, what's going to happen is we're just going to measure both of the first 2 qubits in the computational basis, okay? And then we want to look at what the state is in each of the 4 cases. Just going to read them off from here. Okay, so case 1 is that both the measurement outcomes are equal to 0, okay? So what terms do those come from? Right, we've got to take this state, psi, and then we've got to project it into zero, 0 on the first 2 qubits, tensored with the identity on the last qubit, right? So the terms that survive, basically we kill all the terms in this superposition, except for the ones that have 0 on both of the first 2 qubits. What are they? Well, we have the very first term. So we have alpha over 2, 0, 0, 0. And the only other term that survives is this second last term in the betas. We have beta over 2, 0, 0, 1. Oh, wait. And then we need to multiply this by a constant so that it's normalized. That constant is just equal to 2, right? Because alpha squared plus beta squared is equal to 1. So this state is just equal to 0, 0, tensor alpha 0 plus beta 1. Magically, we have ended up with the two qubits held by Alice are now have been measured, so they're just in fixed state in the computational basis. But the qubit held by Bob is in state exactly alpha 0 plus beta 1, which is exactly the state psi that we started with. Okay? Call this whatever. Just overloading my notation and calling too many things psi, so I decided to clarify which ones are different. So that's great, but that's just, you know, we only have a 25% chance of getting those measurement outcomes, right? Because you know, the normalization of this state was a half. We took its inner product state squared, that would be a quarter. So that's the probability of getting that measurement outcome was only a quarter. If we got other measurement outcomes, surely it wouldn't work out. And indeed, that's right. If it was going to be in this state for all the possible measurement outcomes, then it would have just had to originally been in a product state where Bob's qubit was already in that state, and that's just not true. So the other measurement outcomes aren't going to work out so nicely. So case 2, M1 equals 0, M2 equals 1. Okay, so now the terms that survive are the terms where the first qubit is in 0, second qubit is in 1. So we have this third term in the top row. Alpha over 2, 0, 1, 1. And we have this first term in the bottom row, right? So plus beta over 2, 0, 1, 0. So now, after we normalize and everything, this becomes 0, 1 tensor alpha times 1 plus beta times 0. Okay, so it's no longer as nice. Bob's qubit isn't quite in the state psi, but there's still alphas and betas showing up in front of it, right? Like the states 1 and 0 are the wrong way around, but it does seem like that's pretty fixable. Damn it. Why does that keep happening? Case 3, M1 equal to 1, M2 equal to 0. Someone tell me what the terms that survive in this case are. I've done the first two for you. Someone else's turn to have a go. So M1 was equal to 1, M2 was equal to 0. We have this big state psi 2. What are the terms that survive from if you had to do that measurement outcome? Come on, someone.
You have an alpha over 2, 1, 0, 0.
Awesome. Yep. So that's the first part. What about the second part? Second term that survives?
Minus beta over 2, 1, 0, 1.
Awesome. Great. Again, we normalize, so multiply by 2. And we get the first 2 qubits now state 1, 0, because we measured them, and that's what we got. And now we have alpha 0 minus beta 1. Again, it's not our original state, but it seems to have a lot to do with our original state. Very final case. They're both equal to 1. Someone tell me the two terms that survive from psi 2.
Alpha over 2, 1, 1, 1. Beta
Yep.
over 2, 1, 1, minus beta over 2, 1, 1, 0.
Exactly. So it's the last term from the first row, second term from the second row. So we have minus beta over 2, 1, 1, 0. So this becomes 1, 1. alpha 1 minus beta 0. Okay. We can rewrite all 4 of these cases in a very simple rule, which is that the state is just M1, M2, X to the M2, Z to the M1 times the initial state psi. Okay, let's just check that this is true. I just claimed it. So if M1 and M2 are both equal to 0, then we have 0, 0. X to the M2 is just the identity because M2 is 0. Same with Z to the M1. So we just have 0, 0 tensor psi. So look up here, and explicitly we did indeed get 0, 0 psi. Okay, case 2, M1 equals 0, M2 equals 1. So we have 0, 1, and then we have X acting on psi. What is X acting on psi? Well, it takes 0 to 1 and 1 to 0, so it's alpha 1 plus beta 0. Exactly what we got. Case 3, M1 equals 1, M2 equals 0. Have 1, 0, and then Z acting on psi. What does Z do? It puts a minus sign in front of the 1 term in the superposition. So we get 1, 0 times alpha 0 minus beta 1, which is exactly what we found. Finally, there's the case where they're both equal to 1. And in that case, we have 1, 1, and then X, Z phi. Okay. What is X and Z phi? Well, we first add a minus sign in front of the beta 1 term, but then we apply an X, and so the 1 and 0 get flipped, and so we get alpha 1 minus beta 0. Okay. So magically,
Just a
now
very quick question before we go on. What is the? I'm just struggling to see what's the symbol you used for the measurement. Gate? I guess it's not a gate.
Yeah, it's like a measuring dial in a box.
Oh, I see.
Bigger here.
Got it.
Right. I apologize for my artistic skills, but that's like the curve is like the dial, and the line going up is the yeah. Cool.
Yeah, thanks.
In computational basis. Okay. Okay. So then our final step, our circuit's not done yet. Our final step is just to apply, based on, we send the classical measurement outcomes over to Bob, and then he just applies X to the power M2 and Z to the power M1. So the final state at T4 is M1, M2, Z to the M1, X to the M2, X to the M2, Z to the M1 on psi. Anyone tell me a simpler way to write that down?
Just M1, M2 psi.
Indeed. So X squared and Z squared both equal to the identity. Okay, so X to the 2 times M2 is either just the identity if M2 is 0, or it's X squared if M2 is 1, which is also the identity. So these can get crossed out. And then the 2 Z's goes exactly the same way, so they can also get crossed out. So magically, we end up with the 2 qubits held by Alice. Just record the measurement outcomes. But Bob's qubit is in exactly the state psi. Okay. So comment on this, and really the key point is that there is now no entanglement left between Alice and Bob. Right, we started off with this bell pair being shared between them. But by doing the measurements on Alice's qubit, then we destroyed that entanglement. And so we've ended up with just a product state. And this is really key. It means that you can't just I can't just make one bell pair and then keep sending qubits by just sending 2 classical bits. Each time I want to do quantum teleportation with a qubit, I need to have a new bell pair available. Okay, the bell pair is a resource that gets used up. It's a technical term. I'm not going to define it, but it is a term you see all the time in quantum information. It's a resource that is used up in the process. So this sort of process of quantum teleportation, sometimes written as an inequality. A resource inequality. Where we say the following. Okay, so we used 2 classical bits, right? We sent 2 classical bits from Alice to Bob. We used up our ability to do that. If we had some finite number of like 3 messages we were allowed to send from classical Bob, we used up 2 of the classical bits that we were able to send. And we also used up the bell pair. Bell pair is boring. It doesn't even have a bit in the name. So that's normally called 1 e-bit. 1 bit of entanglement that was shared between Alice and Bob got used up in the process. But by using these 2 resources, we were able to send 1 qubit from Alice to Bob. Okay, so the greater than or equal sign means that you can use the first set of resources to achieve the second set of resources. Okay, is that clear to people? Okay, seems like it's clear or everyone is shy. If you're shy and not clear, then it will be your loss, so please shout out.
How literally should we take this inequality? So is this like how do we know, for instance, there isn't a process that can go the other way and generate more information?
I mean, that would be fine. That would, yeah. So you would want to show for it to make sense to use an inequality symbol, you would want to show that it's transitive, and yeah, you want to show that it's reflexive and that it's transitive, right? Those are the 2 properties you need to have what's called a partial order. So reflexive just means that A is greater than or equal to A. Okay, that's true, right? If I can say send 1 qubit from Alice to Bob, I can use that to send 1 qubit from Alice to Bob. Okay, so that one's fine. And the other one is transitivity. Okay, which says if A is greater than or equal to B and B is greater than or equal to C, then it must be the case that A is greater than or equal to C. Okay? Yeah, let's maybe write this down. So reflexive, greater than or equal to A, can use a resource to simulate itself. The other thing we need is transitive. So A is greater than or equal to B. and B is greater than or equal to C implies A is greater than or equal to C. Okay. What does this mean? It means if we can use A, the resource A to achieve resource B, and we can use resource B to achieve resource C, we must be able to use resource A to achieve resource C, right? Again, that's true. I'll just write CNEST simulations. So if we simulate resource C, if we're able to send, say C is a qubit, B is 2 classical bits and an E bit, and then A is something else. So there'll be a nice example later on. Maybe A is 2 qubits and an E bit or something like that. Then we can use resource A to simulate resource B. And in turn, we can use B to simulate C. And so we must be able to use A to simulate C. Okay. Of course, what we haven't shown is you could imagine that you have some resource A that can simulate some different resource B, and resource B can be used to simulate resource A. Right, that's perfectly possible. That just means A and B are equivalent resources. They're equally useful. You can use either one to achieve exactly the same set of things.
I have a quick question.
Yep.
You said that a bell pair represents 1 E-bit, but can you use like a less entangled state to have fractional E-bits, or?
Yeah, that's a good question. Yeah, the answer is yeah. So often we won't actually care about just having 1 E-bit and say 2 classical bits. We'll imagine taking a large number of each. We'll imagine scaling everything in the equality up to some large number of copies. Same thing. It turns out if I have a large number of copies of a partially entangled state, then I can use that to distill out. I can convert that into a smaller number of bell pairs and then back in principle into the original number of, approximately the original number of partially entangled states. This is called entanglement distillation or entanglement concentration and entanglement dilution. And the thing that controls how many bell pairs you get is what's called the entanglement entropy of the state, which is something we'll come across later in the course. But yeah, so the answer is, at least in a slightly more general setting, then yes. Okay. So a sort of natural question that you might ask is, okay, if we can use 2 classical bits and an E-bit to simulate a qubit, what about the other direction, right? Like say I have a qubit and I want to get 2 C-bits out of it. Can I do that? Maybe 2 C-bits and an E-bit. And the answer is that no, you can't, just literally with this written the other direction, this isn't true. But there is a sort of circuit that's morally the opposite direction of this, which is basically you send 1 qubit from Alice to Bob, and you also start with sharing 1 E-bit between Alice and Bob, and use that 1 qubit of communication plus the E-bit in order to send 2 classical bits. Okay, and this is going to be called super-dense coding. If, and this is a big if, entanglement is free, i.e. you have as many E-bits lying around as you want, right? You just have a million of them that you just somehow, you got too many, you over-ordered, demand wasn't there, they're just, nobody cares about them, they're there to use however many you want, then that means that having 1 qubit, being able to send 1 qubit from Alice to Bob is exactly as useful as being able to send 2 classical bits from Alice to Bob. Okay? But this is only true if you don't care about the fact that to interchange between the two, you always need to lose a bell pair. Is that clear to people? Okay, so the rest of this lecture, we're going to see how super-dense coding works. Sort of similar to quantum teleportation. It's like in some sense a flip version of quantum teleportation. So let's again start by just drawing the circuit, and then we'll go through how it works. So we have Alice and we have Bob. Okay, again, they share an E-bit, i.e. there's some bell pair that is half owned by Alice and half owned by Bob. But Alice also has 2 classical bits, which you'll call M1 and M2, like before. Okay. So here's what we're going to do. Going to apply unitary gates to Alice's half of the bell pair, depending on what state M2 is. In particular, going to apply X to the power M2. Okay, so if M2 equals 1, we'll apply Pauli X, power bit flip, otherwise we won't. And then we're going to apply Z if and only if M1 is equal to 1. Okay? Now we're going to take that half of the bell pair and we're going to send it over to Bob. Okay? We were allowed to send 1 qubit from Alice to Bob. This is the qubit we're sending. So Bob now has 2 qubits. And now Bob is going to apply a C0, controlled by the qubit he just received. Target qubit is the one he's had all the time. Then he's going to apply a Hadamard to the control qubit. And then finally, he's going to measure both qubits in the computational basis. Okay. Is everyone clear on what all the steps in that circuit mean? Okay, again, let's draw, maybe I'll do them in a different color this time. Let's draw a load of different times in here. So we can track what's happening. So T0, T1, T2, T3, T4, T5. Okay. So at T1, sorry, T0, the quantum state, well, someone tell me the quantum state. Come on, guys, someone say this.
It's just a bell state, right?
It's just a bell state shared between Alice and Bob, exactly. We also have a couple of classical bits, but I don't feel the need to write them down. They're just always going to be M1 and M2. So the state is phi plus. Okay. What about a T1? So there's now 2 cases, right? The state is going to depend on what M2 is. If M2 is equal to 0, what's the state going to be?
No change.
No change, right? We only apply this X skate if M2 is equal to 1. So if M2 equals 0, it's still phi plus. What about if M2 is equal to 1? Well, then we apply an X. So it's X phi plus. Okay. What does X do to phi plus? Well, it just takes 0 to 1 and 1 to 0. 1, 0, plus 0, 1. There's a name for this state. Anyone know what the standard name for this state is? It was mentioned in the previous lecture, but only briefly.
Psi plus.
Indeed. Okay, we normally call this state psi plus. Okay, and it's orthogonal to phi plus. Very easy to check. Okay, so this is T1. What about after T2? So now there's 4 cases. M1 equals M2 equals 0. What's the state?
Psi plus.
Phi plus, I think you meant.
Phi plus, yeah.
Right, again, we've done nothing to it. It's still in phi plus. Awesome. Okay. If M2 equals 1, but M1 equals 0, what's the state?
Phi plus.
Yeah, so again, we had done something to it in the previous step, but now we're going to do nothing to it because Z to the M1 is just the identity. Okay, so it's just going to stay being psi plus. Case 3, M2 was 0, M1 was 1. What's the state going to be? So it was phi plus after the first step. We're now going to apply a Z to it, because Z to the M1 is just equal to Z. So if I apply Z to the 0, 0 state, what do I get? Z acting on the first qubit to the 0, 0 state. Someone?
0, 0 state.
0, 0 stays 0, 0, but what about 1, 1?
Minus.
Goes to minus 1, 1. Okay, so we just flipped a phase of the 1, 1 term, and this state is normally called phi minus. Okay, again, it's orthogonal to both phi plus and to psi plus. Final case, M2 equals 1, M1 equals 1. Okay, so now it was in state psi plus, and we're now going to apply a Z to it. Okay, so psi plus was 0, 1 plus 1, 0. What happens to 0, 1 when we apply Z to the first qubit? Come on, someone.
Say 0,
1.
Stay 0, 1. What about 1, 0?
minus.
Gets a minus sign in front of it because the first qubit is in state 1. And so this is, as someone said in the chat, psi minus. Okay. So the key point, which is why superdense coding is going to work. The rest of the circuit is just, bookkeeping. Like the core trick has already been done. Is that we now, depending on what M1 and M2 were, we now have 4 states that are all orthogonal, right? These 4 states form the Bell basis. They form an orthonormal basis, phi plus, phi minus, and psi minus. Now, once we've sent the 1 qubit held by Alice over to Bob, then Bob will now hold both of the qubits. And that means, in principle, he can do a measurement just in this Bell basis that will then be able to distinguish all 4 states, and he'll be able to work out exactly what M1 and M2 were. Okay? The rest of the circuit is just because it's convenient to, rather than having to talk about measuring in this entangled basis, to just convert things so that it ends up being in the computational basis. Okay? So let's just write down the 4 cases. 0, 0, 0, 1, 1, 0, 1, 1. Set time, T2. The state was phi plus, psi plus, phi minus, psi minus. What about at time T3? Okay, so if we're going from T2 to T3, we apply a control not, okay, where the control qubit is the first qubit. So what is that going to do to phi plus, to 0, 0 plus 1, 1? We apply a control not. 0, 0 goes to
0, 0.
1, 1 goes to, come on.
1, 0.
Yep, 1, 1 goes to 1, 0, it gets flipped, okay? So what is 1 over square root 2, 0, 0 plus 1, 0? Oh, it's just plus tensored with 0. Okay. What about if it's psi plus? So the state is 1, 0 plus 0, 1. 1, 0 goes to 1, 1. Yep, 0, 1 goes to
0, 1.
Awesome. So that just means we have plus tensored with 1. Phi minus state, we have 0, 0 minus 1, 1. 0, 0 goes to 0, 0, as we said. 1, 1 goes to 1, 0. So we end up with 0 minus 1 minus state, tensored with 0. And finally, of 0, 1 minus 1, 0. So that goes to 0, 1 minus 1, 1, which is minus and then 1. Okay. Finally, T4, we apply a Hadamard to the first qubit. Hadamard takes the plus state to the 0 state, so it becomes 0, 0, and 0, 1. Takes the minus state to the 1 state, so we get 1, 1, so 1, 0, and 1, 1. Okay. Magically, all we now have to do is measure qubit 1 gives M1, qubit 2 gives M2. Okay. So that's really the main stuff I want to talk about today. It's natural ending point, so I think we'll just end pretty soon. Just going to make a couple more comments about this whole thing. First thing to note is that the outcome is completely deterministic, right? So we often like to think, you know, there's this sort of pop sci notion, which is pretty accurate, that, you know, quantum computers are probabilistic things. You only ever have like a high probability of getting the thing you want to happen. And that's pretty true. You know, a lot of the like real algorithms we're going to see later are probabilistic, but there's also things out there that you can do quantum mechanically that are completely deterministic. On the other hand, the sort of intermediate measurements when we did quantum teleportation were completely random. So the reason the quantum teleportation process worked is that we sent those 2 classical bits from Alice to Bob, yet those bits themselves that were able to perfectly transmit a quantum mechanical state in some sense were themselves completely random and didn't depend at all on what the state psi was, right? No matter what the state psi was, we had 25% chance of getting each pair of measurement outcomes. There is a certain sense, there's a paper actually by my PhD advisor, Patrick Hayden and David Deutsch, that talks about trying to understand how really those classical bits should be thought of as containing the information as it's being transferred across. But in the most literal sense, if you just have those 2 classical bits, then they don't contain any information at all. Final comment is that, yeah, in both cases, the entanglement was absolutely crucial. Oops. In particular, if I'm sending a quantum qubit from Alice to Bob, and I don't have a shared bell pair in advance, then the number of classical bits I can send is at most 1. Okay, there's a reason it's called like super dense coding. It's because the normal, without this entanglement, the most you can encode in you can only encode 1 classical bit in each qubit. Okay, that's really all the comments I want to make. It's about 10 minutes early, but yeah, I think we'll probably just leave it there. I will stick around for questions. People have them, and yeah, next time we have quite a lot to cover, so we'll see. Maybe we'll end up overrunning then, but it's a very different topic, so I don't want to start it now. So yeah, thanks everyone.